Oh, I have the same video problem I heard Stephen talking about. I won't turn it off again. Can I have my permissions back again?
Okay.
Just temporarily.
I will just put you immediately.
You can just put it.
Just a second.
I won't turn it off.
Great. Just excellent. I do not know why this happens. Okay, we welcome you all in another, this is already 13th edition of the One World YoungStats webinar series. The webinar series is part of the YoungStats project, which takes place in the framework of the Young Statisticians Europe initiative of the YoungStats Association and is supported since its start by the Bernoulli Society for Mathematical Statistics and Probability, as well as the Institute of Mathematical Statistics, IMS. Today, we will discuss applied instrumental variable models, IVs. IV is one of the most important and widespread research design in economics and statistics, as it can identify causal effects in the presence of unobserved confounding. Over the past 30 years, the science of IV has advanced considerably, in part through the contributions of Nobel laureates Joshua Enquist, Guido Immens, and James Hickman. Recent years have brought significant advances in how IV is applied in shift chair designs with judge or examiner instruments and in settings with rich or complex controls. In today's webinar, selected econometricians will present their recent works on applied IV methods, and we have, I will say, great pleasure to have with us Kirill Borusyak of University College London, United Kingdom, Paul Goldsmith-Pinkham from Yale University, United States, Stephen C. Coussens, Columbia University, USA, and Alexander Torgovitsky, University of Chicago, USA. I need probably not to say all PhDs, even professors, so I will rather not go into titles. I hope this is okay. And as discussant, who naturally jointly prepared the webinar and with great support, Dr. Peter Hall of Brown University, USA, who will discuss the presentations at the end. So without further ado, I give the word to Kirill Borusyak, who will speak about shift chair IVs and other composite instruments. Kirill, please.
Thanks a lot, Andrei. Thanks both to you and to Paul for having me on this panel conference. I don't know how to call it, webinar. Do I have the rights to share? Yes. Okay, great. So let me just share the screen. Through this very competitive procedure, Peter selected a paper which is joined with himself. So this is what I'll mostly talk about based on our previous work with Xavier Jaravel as well on shift chair instruments. And given that this is a seminar on applied IV, I will not talk about IV until in a bit, but everything I'll say about reduced form regressions in a moment will apply to IV. So keep this in mind. So this is based on this paper that we wrote, which is called Non-Random Exposure to Exogenous Shocks, and I want to highlight the title because it has this color coding, which is important. So throughout the next 20 minutes, what is in red will be a non-random exposure is a bad thing, and what is in blue is exogenous shock, the good thing. So let me start. So we'll be, like Andrei previewed, we'll be interested in situations where you want to estimate causal effects of treatments, let's call them XI, or use some instrument to instrument for other things, but let's get to that a bit later. But in a particular class of settings where your XI is a composite variable computed from multiple sources of variation with a known formula. I'll give you 4 examples in a moment, but kind of our question in this work is how to estimate these causal effects when some components, some sources of variation are as good as randomly assigned and in blue, while others are not, because in economics, if we find something which is as good as randomly assigned, that's already pretty good. You don't hope that all sources of variation will be. Now let's get specific. So what I'm talking about. Well, example one is shift share variables, in which we also have a previous paper, which will be kind of nested in what I'm talking about here. So what a shift share is a primer. So in a typical example where your observations I's are industries, your right-hand side variable, or maybe an instrument, is constructed for region I as a weighted average or sum of some national industry shocks weighted by the local composition of different industries in terms of employment or whatever else. So X could be your regional measure of competition, growth in import competition with China based on industry level import competition with China and the local share of different industries. And so maybe you have a natural experiment that due to some internal policy changes in China, there is growth of import competition of exports from China to the US and other countries in certain industries and not others, as good as randomly. But you are interested in the effects of the regional variable, and the regional variable also depends through this simple formula on the local employment shares, which you are not willing to assume that are as good as random. It's not part of this Chinese policy experiment of like entering certain industries more than others. A second class of situations where this kind of setting applies is any spillover treatments. So in my favorite example of the famous paper of Miguel and Kramer about deworming kids in Africa, maybe the interested in the spillovers of this treatment, and so your X is not your own deworming status, but the number of your friends or neighbors who have been dewormed. And so again, the number of your dewormed friends is simply computed, but from two sets of things: from who gets selected for deworming, for the intervention, and that's as good as randomly assigned according to some protocol, maybe very simple, or maybe some two-tier randomization schemes that economists these days do, doesn't matter. It's as good as randomly assigned. But the number of treated friends for a given person also depends, of course, on who is friends or neighbors with whom, and that is not part of the same experiment, right? That is given and not randomly assigned. Example number 3. So I'll, the next two examples will be what I'll focus on in the next 15 or whatever I have minutes. So when you're studying the effects of new transportation, like railroads or roads, these days, what people in economic geography do is to put as a right-hand side variable X, not just a dummy that a railroad has arrived in your region because it doesn't summarize everything about the railroads, but a kind of a more theory-driven summary statistic, which is called the growth of market access. So basically, a set of railroads have potential to improve things in your region if they get straight access for you to big markets in different parts of the country. And so that's what you want to run the regression on. That's what you want to estimate the causal effects of. And I'll show you the formula for market access in a couple of minutes. But ultimately, it depends on two things. It kind of combines two things: where and when these new railways went, but then also where the big markets in the country are. And so again, maybe you have some natural experiment in railroads. Maybe the timing is as good as random between different lines, or maybe something that, here I highlight the timing in blue, but, in another situation, maybe the location was chosen randomly out of some set of alternatives. But certainly other things like where the big markets in the country are, that's not in any sense as good as randomly assigned. And then the final example for now, although there are a lot more in the paper, and we're always happy to talk about your other applications, will be from public and health economics. If you are interested in estimating the effects of some eligibility of some public program like Medicaid, the public health insurance program in the US, sorry. And so again, eligibility to the program for an individual can be thought of combining two sources of variation: the state level policy of what kinds of people get eligible, but also the individual's characteristics like income, demographics, family structure, all those things that you need to combine together and see if a given person is eligible. It's kind of a useful way to separate these things in case where maybe you have some state level policy experiment of some states like expanding access to Medicaid to new groups while others don't. And so in that case, there is a state level policy experiment, but also non-random exposure of different people to these policy rules, right? And of course, things like income are not as good as randomly assigned. They may be correlated and likely are correlated with the potential outcomes, like with what, how this person's health status would have been without Medicaid. And so in all of this, and by the way, I was again talking about just reduced form, but you can think that this individual eligibility for Medicaid is just an instrument for take up of Medicaid, if that's the endogenous variable you're interested in. The same lessons will apply. And so in this work, in this line of work, actually, including our shift share paper, we're interested in how to estimate the effects of such X, or use them as instruments, while avoiding non-experimental assumptions, in particular, parallel trends based on exposure. So parallel trends between rich and poor people, between kids with many friends and few friends, between central regions in the country and peripheral regions, and so on. So if you've got something which you call blue, which is a natural experiment, or maybe even better, a real experiment, then how to leverage that and nothing else for causal identification. And so what we show in this work is that if you do nothing, if you just run OLS or IV without thinking about this, then this non-random exposure will generate problems, will generate systematic variation in your X, which can lead to emitted variable bias. Even though your blue shocks are as good as randomly assigned, even if in the best possible kind of meaning of the word. That's a problem. The solution is to remove the systematic variation in X, and for that we propose this simple but novel procedure called recentering. In the shift share case, we have kind of a simpler version of that in the previous paper, but this is more general.
Kirill, yep. May I just shortly interrupt you?
Absolutely.
There is a question in the chat.
Oh.
Is X the exposure or the IV?
No, exposure is everything, what we call exposure. There is a bit of terminological differences here. What we call exposure to the shocks is the red stuff. X is the right-hand side variable, or an IV for right-hand side variable, which combines both things according to this known formula.
Okay, thank you.
So for us, exposure is like, your individual income and demographics as exposure to the shocks to the state level policy of who is eligible, for example. That's the terminology we use.
Okay, thanks.
Okay?
Thanks.
Yeah, so back to how to solve the OVB problem. The key step here is to think about and specify many sets of counterfactual blue shocks. So who could be selected for deworming instead of the people who did? Well, that's easy, right? We randomized, or Miguel and Kramer randomized who is dewormed, so you can re-randomize many times. Or what the maps of these new railroads could have been instead of the ones which have been realized. That's a bit more challenging. I'll show you how to do it in a moment. But once you've taken the step of thinking what actually variation you want to use, like in the shocks relative to some counterfactual shocks, then everything else is straightforward. You just need to recompute your X, or your instrument, under all of these counterfactuals, holding exposure fixed. And then average across, let's say, 1,000 of these counterfactuals, what is the average X this region, this individual gets across the various counterfactual shocks. That's what we call μi, as the expected treatment to expected instrument. This is done by simulation from redrawing these counterfactual shocks. And we show that this is the key confounder which creates the emitted variable bias problem. And so removing it removes the OVB. How does it work? Well, that's what we call recentering. You instrument the X with the component of X, which is over and beyond the mu, the expected X. Or if you start with an instrument, then you replace the instrument with the component of the instrument over and beyond what this person or this region could expect. Controlling for the mu is another very similar solution that works as well. We also show many things in this work that alternative solutions are typically infeasible or inefficient. Think about shift share. You can't really use an instrument, an industry level variable as an instrument for your regional variable, right? You need to convert it into regional space, and so that creates these problems. And you also can't just control for all the red exposure. If you control for all the shares, you will run out of all variation in the shift share case. And then we show also how the same counterfactual shocks can give you confidence intervals and balance tests, but I'll skip that. I don't have much time. Actually, I don't have much time at all. I mean, we started a bit late, but maybe I have 10 minutes at most, right? So
Yes,
let me do,
yes,
yeah,
just
thanks.
no problem.
So let me show you a motivating example, and then some formal results in one slide, and then a bit of the applications. And so this will be about market access indeed. Standard models of economic geography give you this very simple log linear equation saying that the outcome growth, like employment or land value or whatever in a region, depend on the railroads through this summary statistic market access. What is that? Market access is a sum across various regions J in the country of their market size, like population, inversely weighted by the travel time. And the travel time is affected by the transportation available, GT in this period, and also, of course, the locations of I and J. And so imagine, to just illustrate, use the key intuitions, imagine the best possible experiment here. You want to estimate the beta. There is nothing to estimate in the second line, it's just a formula. So you want to estimate the beta, well, you randomize roads. Imagine you can randomize them completely, dropping them from the helicopter. And so in that case, market access will grow just because of these new totally randomly drawn railroads. So you can think, oh, let me just run a regression and think that I'm using this variation from railroads to estimate my coefficients. And the answer is no, you can't. Randomizing roads doesn't mean randomizing market access growth due to them, because the formula for market access includes all these other things like populations, locations, and so on. So here is my simple example, a map of a country, which is just a simple square, and I drop roads from a helicopter. I compute market access. Of course, it's higher where railroads went. But if I redo this 1,000 times, if I redraw railroads, recompute market access on average, I will see that it's not the same on average. The central regions here get more market access intuitively because they're kind of closer to many potential railroads. And so the center of the country will systematically be in the treatment group on average, while the periphery will be on the control group. And the fact that you randomized railroads from the helicopter doesn't make those things comparable. What is comparable is regions where market access grew more than this picture to regions where market access grew less. And that's exactly what our recentering procedure does. It exploits, exactly where the railroads went to construct this component over and beyond the expectation. So red here means that your region got more than expected, and blue means less. And so that is the treatment and control group our recentering procedure uses. It's not just about centrality and periphery. Here I have a map of China where our application is with 150 lines which were planned, high-speed rail lines. Out of them, only 83 are built by 2016. And so if you imagine, again, for simplicity, I'll do better in the application, that the timing was completely random. Any 83 could have been built by 2016 out of the set of the planned ones. So even then, again, it's a simplified case, and still, I can then redraw 83 lines many times, recompute market access, take the average. You will see that there are complex patterns of where market access systematically grows because of which regions are close to big markets, close to many planned lines, and all of those things, which are hard to just deal with by some ad hoc controls. We recommend that this procedure kind of computes this variation, and then of course you recenter by it, you remove this and use the variation on market access over and beyond this. Let me spend 1 minute on the formal setting or formal language we developed to think about this. So we'll, in the baseline, just look at the simple linear equation y equals beta x plus epsilon for some fixed set of observations i's. You don't need random sampling here or anything. The setting generalizes to heterogeneous effects, to having multiple treatments, like a direct effect of deworming and a spillover effect at the same time. All intuitions go through with panel data and so on. And so we'll start with a candidate instrument. I've been telling you that it can be a right-hand side variable or an instrument, z, which is a function, a known formula fi, which depends on two things, and it's your researcher's separation of them, which is just useful. G as the shocks, the set of shocks arising from some experiment or natural experiment. There are not n of them, but some k, so they could be across industries or across whatever lines. and then W is everything else. So this just tells you that you can compute your candidate instrument from the data you have, which you split into these two components. And of course, if X equals Z and has a structure, then you are in the OLS world. And so we'll impose two assumptions. One is exogeneity of the shocks. Formally, that the vector of shocks is statistically independent from the vector of error terms given exposure. So that's as good as random assignment in a sense. And second is that the distribution of the G of the shocks given exposure is known. And when I say this, I don't mean that the distribution is like Poisson or whatever. I mean, you can redraw from this distribution. In an RCT, you always can. Outside RCT, typically you would redraw by doing some reasonable permutations, which you think were as likely as the one that realized. So permuting, reshuffling lines which were planned and built versus planned and unbuilt, if you think that the timing was random, for example. Or permuting like industry China shocks across industries, if you think that China just entered randomly. You can do it with controls or whatever as well. And so in that world, we can define our mu, our expected instrument or treatment, mu I, as the expectation of this candidate instrument given exposure across the known distributions of the shocks. It's implemented by simulating those shocks. And then we show that the recentered instrument Z minus mu always satisfies the moment condition. It's orthogonal to the epsilons. And so as long as it has power, which typically it will give you the a consistent estimate of the beta. I'm running out of time, so I don't have really time for the application. We take it to a Chinese high-speed rail where we do something smarter than just thinking that China was randomizing the timing of lines. We say, no, no, no. We would think that they reshuffle, that they the timing was random, not across all lines, but only similar lines. So if you've got several lines which are similar in some observables, then maybe the fact that one got built earlier than the other, even though they were both planned, maybe that's as good as random. So we'll use that to recenter, and we'll show that this very strong positive correlation between the growth of market access and employment growth actually disappears then. It doesn't matter whether the lines have been built or haven't been built yet. You still, if you are well exposed, you're still getting this employment growth. So the coefficient mostly goes away. What I want to spend the last minute on is the second use of our framework, which is not for bias that I've been mostly talking about, but for efficiency. The idea here is that in some cases, among those which I mentioned, you could just instrument with the shocks and ignore all the non-random exposure you're worried about. We're saying that's very inefficient. And the setting where we can show this is Medicaid. So here we look at the expansion of Medicaid in 2014 under the Obamacare Affordable Care Act, where out of 43 states which didn't have generous Medicaid yet, 19 decided to expand it to some standard national level. And so we'll view the states which expand and don't expand as good as random within Republican states and Democratic states separately. And so that will give us these permutations that we can use. Now, of course, the problem is that individual eligibility also depends on all of these income and demographics. And so the standard solution, which is called simulated instruments from Curry and Gruber, is just to use the variation in the shocks, right? Just to use state level variation and discard all of this non-random exposure, income, and so on, which are non-random. And that's fine, but very inefficient. What we propose instead is to get a much better first stage, much better prediction of eligibility from everything, from the shocks and from the decisions to expand and individual demographics, which pretty much gives you a precise prediction of the individual eligibility, but then recenter. So the second lesson from this work is that you don't need to be afraid of non-random exposure. You just need to take it seriously and recenter by it. And we show that this leads to about 3 times smaller standard errors for all outcomes we look at. So that's 9 times smaller variance. Really, it makes a difference to get a better first stage. All right, I'll stop here. So we, developed this framework for treatments and instruments computed from multiple sources of variation. I've showed you a few examples, but there are many more. We show that if one source of variation is as good as random, but others are not, then there is one variable you need to compute, that's the expected instrument, expectation taken across counterfactual shocks. And that's feasible as long as the researcher is willing to actually think seriously about what the natural experiment is, right? If the shocks are random with respect to what are the counterfactuals. And this is empirically relevant. I'm happy to take any questions and look forward to Andrei's discussion. Thank you.
Thank you. Great, thanks. Kirill, naturally, virtual clap. I do not even see how to make it here, but thank you for a great presentation. Before we continue, we need to continue, but just one short question. You have several of them in the chat. Gamma asks, how many simulations are enough to compute the parameters? What if there are some variation? Is there some estimation on the number of simulations that you need?
So we don't have any formal results on that. In practice, I mean, you just need to estimate this mu, right? And adjust a control or something like a control. So in practice, we find that it converges very quickly. So if you, we do 1,000, but if you do a few hundred, that's enough. But it's something you can easily check in your application as soon as you see that the mu doesn't move anymore. If you double the number of the simulations, you are done. Now, importantly, this assumes that there is a rich enough natural experiment, right? If the entire experiment is that there are two possible maps of railroads and you're choosing between the two, well, that's not going to give you a consistent estimate, or typically, at least without extra assumptions. But as long as you have a really a lot of things to permute, that's not a problem.
Okay, thank you a lot. Thank you again. Great clap, and we would continue with Stephen Coussens. Stephen of Columbia University will speak about on efficient estimation from compliance weighting. I think it is a joint paper with, just a second. It's a joint paper with Jan Spies, but I'll leave you the floor. Thanks.
Thank you. Great. Let me go ahead and pull this up on screen. And there we go. Can everybody see this okay? Okay, great. All right. So thank you so much for having me. I'm very excited to be here to discuss this work with Jan Spies. We've been working on this for quite a while, and we're looking forward to getting feedback from you all. So ultimately, you can think about this paper as thinking about how do we improve the precision of IV? Because as Kirill had pointed out, there could be a lot of sort of precision gains from more fully exploiting the variability in exposure, right? So let's think about at a very high level. We know that there's this tie-in for prediction in the first stage in IV. So we can think of two-stagely squares, for instance, as being related to this prediction problem, where in effect we predict the treatment D from instrument Z, then regress outcome Y on those predictions. And so this has led to the use of machine learning for high-dimensional instruments. Yet oftentimes in practice, and as a very applied person, this resonates with me, that instruments are often very simple, say a randomized control trial or RCT with binary treatment. So what our paper is really about is how can we leverage simple instruments with high dimensional pre-assignment covariates? It's often the case, especially with the kinds of administrative data that we have access to these days, that we have pretty rich covariates about, say, participants in a trial or quasi-experimental study, but the treatment itself is simple. So how can we use those covariates in a data-driven manner to improve IV inference? So we'll think about a very simple setup just as motivation for this paper, which is say an RCT with a binary instrument Z, binary treatment D, and as I'm sure you're all familiar with the compliers, always takers and defiers categorizations and thinking about the late. The important thing to keep in mind is, although as usual, we're going to make the assumption there are no defiers, and that is an assumption here. Only the compliers are actually contributed to the IV estimate, to that late, right? The always takers and never takers are in effect just adding noise to the estimation process. So I'd like you to consider just a very simple, straightforward thought experiment. Suppose you had two studies that each had 1,000 compliers. So study A has 1,000 observations, so in other words, 100% compliance rate. Study B has 4,000 observations, so in other words, a 25% compliance rate. So all else equal, how does IV estimator variance differ across these two studies? And for now, we're going to assume constant residual variances. Well, I think oftentimes we kind of have this heuristic understanding in the back of our head that, oh, as sample size gets bigger, our estimates are going to get more precise. But that's not strictly the case when we're thinking about IV, right? So the variance is in fact proportional to n over the number of compliers. So in other words, the variance holding the number of compliers in this study fixed is linearly increasing in the number of observations, right? So what this means is that the variance in study B is in fact 4 times larger than in study A. So in other words, if we were able to perfectly identify all of the compliers in study B, we could reduce its variance by 75%. So the basic idea is, well, let's use the covariates to locate the compliers. So as I said at the outset, IV estimation is often pretty noisy. And so we want to figure out, okay, how do we leverage these simple instruments with some potentially high dimensional covariates to improve IV inference? Now, the first way we'll consider is thinking about weighted IV, where the weights are a function of these covariates. You could think about the efficient weights, and we'll go into more detail a little bit later, as being the local strength of the instruments. In other words, the compliance rate itself. Now, interestingly, the compliance is itself a conditional average treatment effect, right? It's just the first stage conditional average treatment effect, which means, though, we can use some of these really nice non-parametric machine learning techniques to estimate this first stage conditional average treatment effect compliance. So as we'll talk about a little bit later, things like causal floors, which you may be familiar with. And then we want to be able to, sorry, I just had a pop-up. We want to be able to conduct valid inference based on an adaptive estimate through sample split. So I want to point out that our paper relates to a number of literature, some of which are still very active, including the paper that Kirill just presented. But obviously in the constraints we have time-wise here, I'm not going to go into detail on discussing our connections to them here. Okay, so moving forward, I think our main contributions can be summarized as follows. In a potential outcomes framework, we provide robust implementation and inference tools that continue to work even when the weights are estimated non-parametrically. And also, we motivate weighted IV from instrument interactions as well. So basically demonstrating this weighting interaction equivalence that we'll return to a little bit later. So returning to the simple binary instrument binary treatment setup that I mentioned earlier, the assumptions that we're going to be making are standard IV assumptions, including the exclusion, restriction, relevance, monotonicity. The strong assumption that we're making here, though, is the random assignment of Z itself. So again, thinking analogously to a randomized control trial. Now, in this setting, tau, which is the late, the IV estimate, is as follows. The canonical IV estimate is just the covariance of the outcome in the instrument divided by the covariance of the treatment and the instrument. And the canonical IV estimator is just the sample analog of, right? Now, if we're thinking about how we can use pretreatment controls, there's a number of ways we could go about doing this to try to improve precision. Say we could use a non-parametric residualization. We could try to generate weights to reduce the variance. And as I'll return to a little bit later, we could also consider using the covariates to create new instruments by interacting functions of x and z. So just notation-wise, I use tau of x here to denote a conditional late, conditional on x, and conditional compliance alpha of x. So in the paper, we derived the asymptotic distribution of this weighted IV estimator. And I think the important thing is to keep in mind how to think about this estimator under various scenarios, depending on whether, say, we allow treatment effects to vary. Things like that. So in general, we have an estimate for this weighted IV estimator as follows, this tau W, and the variance of this weighted IV estimator, asymptotic variance of this weighted IV estimator, VW. So under treatment effect homogeneity, so in other words, constant treatment effects, you minimize the variance of the late by weighting, by assigning weights that are equal to the compliance divided by the conditional residual variation. And so this is similar to the efficient instrument in the paper that we just saw Kirill present. And in addition, if the residual variation is also constant, then we can see that the optimal weight is actually simply just weighting by compliance from a variance minimization perspective. Right. Now, things become a little bit more interesting if we start thinking about the world in which treatment effects are not constant, because in this case, the estimate itself is actually affected, right? Now, if you think about what say the late actually represents, it's just a case where the weights themselves, of course, are fixed, right? If we were to use just compliance weighting, as I just mentioned earlier, then this would correspond to, in effect, doubling down on the compliance weighting that's baked into IV. In other words, squaring the compliance weight. You could also consider, well, perhaps what if we weighted by the inverse of the compliance propensity score in an attempt to sort of back out the 8? So in essence, when you're thinking about these different perspectives, you could think about facing this trade-off between external validity and variance in estimation. Right? So I think a very neat aspect of our paper, something I enjoy, is thinking about this, how optimal weighting fits in with thinking about an alternative approach to improving IV precision, which would be to try to optimally interact instruments or interact functions of covariates with instruments. So we show in our paper that every valid instrument takes the following form, right? This h of x and z is in effect a weighting of the mean instrument. So for such an instrument, we actually have equivalence between the interacted estimator and a weighted estimator. And the nice thing about this is among these instruments, the choice that minimizes the first stage mean square error is in fact the compliance, right? And this is in a world in which there's constant residual variance, also minimizes the asymptotic variance of the estimator itself. Now, of course, unfortunately, the known population weights are rarely given to us, and so we must estimate them. And so I think a major contribution of our paper is thinking about, all right, well, if we're using these non-parametric tools to estimate these weights, how can we conduct sort of valid inference from the estimates we get? And so we can start by thinking first about, under this constant residual variance framework, we have the compliance alpha of x, as I mentioned earlier, is a conditional average treatment effect in the first stage. And so we suggest using tools like the causal force to try to estimate that. And we use cross-fitting as part of our implementation to avoid bias, right? So using a k-fold sort of cross-fitting to obtain the compliance weighted, to obtain estimates of the compliance weights. And then we just calculate a weighted two-stage least squares to estimate this compliance weighted estimate. So you could imagine, though, at the same time, say, if there were also variation in residual variance, then we could estimate that as well. And there's a literature on thinking about feasible GLS using machine learning tools as well. And so then in that case, the optimal weight would be the compliance divided by the residual variance. Now, for the asymptotic distribution in the homogeneous case, things are relatively straightforward. As I mentioned earlier, the estimand is going to be the same as, say, two-stage least squares, right? It's going to be the late. In that case, with cross-fitting, we can use machine learning tools to estimate these weights, and we know that it's going to be centered around the late, and we have like this asymptotic variance here. Now, so under these same conditions, we still have the consistency of this estimator for the weighted estimand, but we have somewhat of a challenge for asymptotic normalities, since now the estimand depends on the weight itself. And these weights are estimated potentially lower than a parametric rate. So our approach is to condition on as much as possible, considering an estimand with empirical weights. So in other words, using these cross-fitted weights to sort of like center the distribution. So in that case, we're able to demonstrate asymptotic normality with respect to the empirical estimand. But I'd also like to point out that if the variance of the treatment effects themselves is bounded, then even without conditioning on the empirical estimand, we're able to achieve asymptotic normality. So now just briefly, how am I doing on time? Okay, great.
About 5 minutes, maybe.
Okay, great. So I'll briefly now discuss just some simulation evidence for how this all works out in practice in terms of when using this approach is likely to produce the most gains in efficiency. So in the setup we have here, it's pretty simple and straightforward, but we're just thinking about a world in which we have imperfect compliance, say in an RCT. We have 10% always takers, 65% never takers, and about 25% compliers. And so in this case, we want to use the covariate X to try to predict compliance rates, come up with estimates of the compliance rates, and then use those cross-fitted estimates of the compliance rates as weights in order to estimate the late in this case. So what you'll see here is relatively intuitive. It's basically telling you, as you move from top to bottom, as it becomes easier to estimate the compliance, that is, the less noise you have in the first stage process and the more heterogeneity in compliance, observable heterogeneity in compliance that you have, the better the improvement of precision is going to be. So like in this case, you can see off to the right-hand side here, you have like what the naive OLS estimate would be, centered around the wrong, sort of centered away from the late. And here we have both compliance weighted and unweighted two-stage least squares estimates. As you move from top to bottom, what you're effectively seeing is, as it gets harder and harder to predict compliance, there's less and less difference between these two approaches, right? And again, you're seeing the same type of thing here, just represented in terms of the root mean squared error of unweighted versus compliance weighted IV under a few different implementations. So at the bottom here, you see like we've like estimated these compliance weights using both, say, cross-fitted honest causal forest as well as like a linear OLS model, and ultimately, which is sort of the optimal choice is going to come down to the nature of the prediction problem, how non-linear the relationship between compliance and the covariates are. And so in effect, the more precisely you're able to estimate the compliance weights, the more precise your IV estimates are going to be. So in summary, I'd say the key takeaways are just thinking about, well, IV regression reduces bias, say, relative to a naive OLS estimate, but it's often very noisy, and this has been pointed out throughout the literature. So for high dimensional instruments, we can try to improve the precision with non-parametric regression in the first stage, but if the instruments are simple, we can still do, in many cases, a much better job by efficiently weighting for binary instruments in the late framework, like we do here, implementing a sample splitting and non-parametric and harnessing non-parametric methods to estimate these compliance rates, taking advantage of what could be potentially rich covariates. And we provide asymptotic theory and tools for valid inference, so these can be implemented in practice. And we also relate this to optimal weighting, to an optimal interactive instrument framework. So that's all I have for today. Thank you so much, and I look forward to hearing your comments.
Thanks. Thanks, Stephen. Great presentation. Thank you. We will continue, but just a short question. I see several of us have the almost same question. You write in Peter Holt has also written this, and Monica Avila Marques. Does your framework work only with binary treatment outcome, as you write in the paper, or could this be extended also to, say, continuous situations or other situations?
Yes, so in the paper itself, and I believe like it's currently in the appendix, we extend the like interactive instruments framework to multi-valued instruments, and like an approximation to even like continuous by thinking about them as like polynomial functions. And so you can think about applying this approach like more broadly, although strictly speaking, like the weighting approach that we have is relying on the binary treatment, binary instrument framework. But I think more generally, I think this fits in well with Peter and Kirill's paper, thinking about really what you want to do is focus on where the instrument matters. And so like I think like the intuition there is very generalizable. The specific implementation that we have set up right now is focusing on this like discrete case.
Okay, thank you. Thanks again. And I suggest now we continue with third presenter. We have Paul Goldsmith-Pinkham of Yale University to speak about judge-examiner instruments. Thanks. I will just Paul.
Sorry, I'm
Yes, immediately.
so good. I'm here. I'm okay. Let me know. Okay, perfect. I'm getting rusty about my my Zoom. 1 second. So you know I haven't been teaching in a while. Okay. Can you all set? Can you see my slides? Perfect. Let me know if you have any issues hearing me. Thanks a lot, Peter, for inviting our paper onto the program as well. I think, this is an endogeneity bias, but maybe just speaks to Peter's just deep desire to work on things IV related. So this is work also joint, most importantly, with Michael Kolesar at Princeton. And this is super, I don't want to say early stage in the sense that we're writing stuff down and we're hoping to get a draft soon, but I think relative to the last two papers you saw, this is far earlier on. We kind of have the baseline paper that established this work, and we're kind of working to write some of this up. And this is something Peter and I have been talking about for a long time. So I just want to caveat that some of the phrasing of how I'm going to describe the results here are going to sound more vague in part because we're kind of working to kind of formalize these things. And I'm excited both for the types of questions you have and for any feedback. So this is about examiner designs. And so examiner designs, this is one term that gets used, I would say is the kind of the more formal term. A lot of folks would call this something like a judge design or leniency design, something basically in these many varied types of applications. There's an administrator, judge, some kind of monitor who plays basically an important role in deciding an outcome. So judges are super common, but it doesn't have to be a judge. It can be a loan monitor, a loan officer, things like that. There's a lot of really interesting examples that range across a lot of different important cases. Bail, consumer bankruptcy, so that's what I've worked on, getting a loan, parole, disability insurance, whether or not you maintain your patent rights, cancer screening by doctors, lots of interesting cases in which you think who you get assigned. Basically, what's happening is that this examiner or whomever this is randomly assigned, typically conditioned on a large set of controls. And there's a wide range of differences and discretion of how likely they are to decide the outcome, right? It matters who you're assigned to in some meaningful way because there's just heterogeneity. And so the key ingredients, if you're a person thinking about this and you're working on this and you want to know, am I doing this well? The key ingredients are this random assignment of an examiner, there's discretion. Typically it's a binary outcome, but that's not really necessary. And binary endogenous variable, but that's not typically necessary, and some kind of heterogeneity there. So that's kind of like intuitively what's going on. What I wanted to kind of do today is it's a little challenging to write the slides for this talk and a little bit challenging of what we're putting this together. Is a combination today of what we're talking about is going to be things that are kind of formalization of some of the things merging between what the empirical literature works on and I think how econometricians would talk about it, that exists. And I think if you ask many folks who work on this, who know some of this, but isn't really in the extant literature in the sense that like, we're just kind of trying to formalize this a little bit more to make sure. Oh, can you still see my slides? No, it said, oh, Andre became the host all of a sudden. You're muted, Andre. Now I'm the host. Okay, great. Sorry. Here we go. Let me try again.
Yeah, please.
Let's try again. Okay. Can you see it now? Okay, we're back to the outline. Okay, good. So this is kind of just, I'm giving a little bit of formalization on a result I think I wouldn't try to claim that people aren't aware of, but I want to make very concrete for folks, and it will help kind of motivate some of the other stuff. Then I want to present considering kind of design-based approach to this examiner setting with in basically the simplest case possible, no controls, where we can show you basically how you should think about what's going on when you use this estimation, what the implications are for inference, and basically discuss the challenges therein, basically give a bunch of answers to what we think are existing questions in the literature. So that's a very high level to kind of talk about monotonicity, exclusion restrictions, and kind of things about inference and other kind of problems that need to show up. And we'll give you some solutions that we're trying to motivate. So that's the outline. That's a very cursory outline of what we're going to talk about. So as I mentioned, you kind of have the intuition of what's going on, right? There's these examiners are getting randomly assigned. Think of the panelists here. For all the participants who are around, the panelists are all these examiners who are potentially getting randomly assigned to you. You're getting different versions of them. The idea in our setting is we're going to have n units. There's going to be random assignment of some examiner Q. So Q is going to be our examiner. There's going to be K of them. So K could be one and it's just two judges, or it could be many of them and there's a big panel like what we have. We're going to have some potential treatment D. We're going to make it binary, and then some potential outcome. And initially, as you notice, and this is quite common in this, is that we're not going to assume the exclusion restriction. So, Y could be affected both by the potential treatment and by what judge you get. And then we're going to have a vector of covariance. So these are going to be potential outcomes, potential treatments in kind of the potential outcomes frame of it, we're going to have random assignment of an examiner, and we're going to have covariates W. So we observe these realized versions of it as a function of what your Q is. And typically, we're going to assume that QI is effectively as if random. So it's going to be conditionally independent, conditional on W. So that's notation of what's going on. Now, let me just make this super concrete. So we're not just keeping track of notation. Is like in the context of my paper with Will Doby and Crystal Yang, what we had bankruptcy judges. You'd show up at a bankruptcy court. You would get randomly assigned a judge in the office when you showed up about your case. That's Q. There could be a couple of them within a given office. And they affect whether or not my debts will be discharged, whether or not I get bankruptcy discharged. I won't get into it what bankruptcy is, but your debts are going to be discharged. And it's basically, there's a certain amount of randomness to it. And we care about the impact of bankruptcy discharge on your subsequent credit score. And we're going to have a vector of covariates that are going to be things like bankruptcy court year fixed effect. So within a court year, we think of the judge as being randomly assigned. So, ignore the covariates for a second, this W, just imagine we're sitting within one court year and we're thinking about the random assignment of judge. That's the kind of content we have in mind, but there could be lots of different settings. So for now, let's think about a single constant. So just within a particular bankruptcy court and a given year. Now, that's the setting. What I want to do first, and this is always a little bit weird, is I want to talk about what is the existing kind of empirical approach that folks will use, and it's quite common, including in my own work historically. So the typical approach is to basically construct a measure of what we would call leniency. So the idea is you have some treatment DI, remember this is bankruptcy discharge in our case, where we'd use two-stage least squares and use a measure of leniency of the assigned judge. So we need to approximate it, this idea of, okay, well, how likely are they to give a discharge? And the way that we would do it is for this Li hat, this is the simplest version of it, is you'd say, okay, well, take all the people who got assigned a given judge, all the people who got assigned Peter, and just calculate on average how many discharges does he do. And then do the same thing for Kirill, do the same thing for Alex, and do the same thing for Stefan. You'd go through all of those and you'd construct different measures for each one of them. There's this slightly more complicated version, which I'm indexing by LO, which stands for leave out, which is you do the same thing, but from my measure of it, I got assigned Peter. Well, when I construct Peter's leniency, I don't want to use my own observation, and so I'll leave it out. And we'll get into why you would do that in just a second. So people use that measure now. I've got this Li measure, and they run this two-stage least square. So you can find a bunch of papers do exactly this thing. You've got this continuous measure here, Li, which is going to vary depending on which judge you have. Now, the question is, well, let's contrast this to what I'm going to emphasize is it's the kind of underlying framework of what's going on, is to say, all right, well, I'm not going to use that leniency measure. Instead, I'm going to, in the first stage, I'm going to use dummies for which judge you got assigned. So examiner dummies. And kind of the key point that if you didn't get this emphasized, you'll have this light bulb moment. And this shows up in other settings too. But basically, the point estimates that you would get here for beta 1 are identical to using Li hat, this leniency measure, in a just identified two-stage least square setting. And so the way you can see that is you just write this down with these Q dummies. If you write down this over-identified setting, remember we have K instruments here. Well, if you write this down, you end up having a projection matrix here in the middle. These Qs are a projection matrix, basically saying project D onto the Qs, which is going to be the fitted first stage values. And they're just the group means. We have a bunch of mutually exclusive dummies. That's something you can work out, but it effectively says, the first stage fitted values from running on a bunch of dummies are just going to be the means. And that actually is what is L hat. And so there's this nice kind of isomorphism between the two of them that makes it very clear, okay, why would you want to use this Li hat? So that's the first thing to kind of keep in mind. The next thing that's kind of interesting is, that was easy. It was easy to kind of write this down. Well, as I kind of alluded to, more people use this leave out method, including my own work. And it turns out using just identified two-stage least squares with this leave out method is numerically identical to using the jackknife IV. So using these examiner dummies. So if you haven't heard of jackknife IV, this is basically an approach by Angrist, Imbens, and Kruger, and follow-up work. They have a Journal of Applied Econometrics paper about it. And the idea here is that it's designed to solve the many weak instrument bias. Basically, this idea that many judges can cause overfitting. And so what you do is you effectively are leaving out your own observation. And so that, as you remember, is mechanically what we're doing with that leave out leniency construction. And so there's this really kind of beautiful intuition that folks are effectively implementing jive, but doing it with this continuous measure. So kind of one emphasis that I have, and I would encourage people to think about in this setting, is that leniency design and examiner fixed effects are not really using different empirical strategies, in the sense that this is all coming from the same. There's no difference there, right? I've kind of shown you there's these mappings depending on what estimator you use. It's just different estimation approaches. So that's kind of the first thing. So it's like important kind of keep that where the variation is coming from. The single instrument LI is typically estimated with error when you have many instruments. It's really a function of how many observations you have. And it's kind of and I don't want to speak fully for my co-authors who haven't written down the words yet, but I think using leniency shrouds that fact a little bit depending on the context. And so estimating the underlying first stage is noisy. You don't want to forget that you have these many, many dummies that you're estimating with. And the last point that's important is jive is not going to be sufficient to solve bias when you introduce many covariates. So this would require an estimator like ujive, which this was something that Michael Coussens, our co-author, emphasized in his job market paper in 2013, is that there's basically when you have many covariates you need to control for, you need to additionally solve for this additional bias problem, this many controls problem. So this is kind of the first, this was the lead up, right? So this was the opening the thing right before the opening credits was kind of the lead up here of talking about what's going on. It's kind of like a full theorem of examiner design to kind of emphasize what's going on, or a point being that really you should focus on examiner dummies as sort of thinking about you have these many instruments. It's a very clean, very kind of beautiful setting in which you have many instruments, potentially weak, lots of interesting things to learn and think about there econometrically. So now if you think about examiner designs and what people do, it is pretty clear that there's kind of some outstanding questions in the empirical setting of how to do these examiner designs. Even though we have random assignment, it's kind of clarity missing on a number of questions. So one of them is just about inference. And so talking to practitioners, and certainly in my own experience is like, well, what are you supposed to do in terms of, are you supposed to cluster? Do you cluster on the office? What covariates do you cluster on? Some papers cluster both on the location and on the examiner, like on the judge. Is that right? The second is, okay, if you're constructing leniency, what's the right dimension to be aggregating over? So I mentioned to you, remember I was saying well, you're going to sum up these discharge for a given judge over a particular period. Well, are you supposed to be doing this in, a dimension in which you do it for a year? Do you do it for a month? What's the right time dimension to be aggregating over if you're going to construct this mean? And lastly, it's how should you think about monotonicity and exclusion? It's sort of easy in the just identified setting, sort of right? If you had the easiest one that we all learn is kind of a no controls, binary instrument, binary endogenous variable. Then we know how to think about exclusion and monotonicity. It gets harder and harder once we have many instruments. What does that kind of mean in this setting? And so what we argue is that kind of using a design-based framework and thinking about these examiner dummies really sheds light on these questions. It becomes much more concrete about what you're assuming and what you're doing. And I think some of what we're saying is going to be new, and some of it is we're kind of pitching a tent for a lot of other papers that are talking about these same things as well. So let me tell you the setting. So what we're going to do is we're going to think about a design-based approach for thinking about estimation. So what we do is we observe these set of things. Remember, we observe Q, the examiner, these covariates W, Y, and D. And Y and D are basically realized values of these potential outcomes. We're going to assume that the potential outcomes and the controls are fixed. And the only thing that's random is the examiner, which judge you get. So this is effectively what it means to be using a design-based setting. For right now, I'm going to say no controls, so we don't have to worry about any of that. And what we're going to do in all the results that we have so far is we're going to focus on the case of an oracle estimator. that uses a single instrument. So what do we mean by that? What I mean by that is, think back to this case of we were estimating the means. So we're estimating these group means for each judge. Well, in that case, the idea is that, well, we know the first stage coefficients. So to actually go back just a second to make this really concrete, I should have written this out, is that remember in this first stage, we have these dummies here. The oracle version of this is that I don't have to estimate gamma tilde 1k for all, for this whole gamma tilde vector. I'm as if I'm God. I know exactly what these are. I am the oracle. I know what the first stage coefficients are. And so now I don't have to worry about estimation error there. It's kind of the best case scenario. And so I estimate this measure. I have this oracle single instrument, which is effectively the first stage fitted value, demeaned first stage predicted value. So given that, once we have a single instrument value, which is this oracle measure, we can think about the Wald estimator, right? This is a just identified setting where we have this tau star. We're going to use this. We're going to think about this is the reduced form on top. This is the first stage on the bottom. And what we can show is that under pretty reasonable regularity conditions converges to this estimand, which is going to be basically this covariance between this D star Y and this D star in the first stage. Now, the question, of course, is like, that's fine. I've just written a bunch of algebra up there. All we've done so far is assumed random assignment of QI. And so there's kind of two things that I'm going to talk about and I'm going to show right now for these results. One is going to be about inference. So like, what can we say about this estimator? So this Wald estimator here, tau star, what can we say about inference? Remember, I was talking about like clustering. What do we do? What are we going to be able to say there? And then second is going to be, okay, well, what can we say about the causal interpretation for tau? So in that setting, as you might imagine, we need things like exclusion restriction, which is to say that the potential outcome is only affected by the treatment and not by what the only way that the judge assignment is affecting me is through what treatment I got, D equals 1 or D equals 0. And then this other one is this monotonicity, is this idea that there exists an ordering of the judge's strictness that holds for all individuals. So first, let me just kind of, before I had this the other way, but I kind of just want to do this quickly because that's kind of tell you this punchline is that under this setting, what we can basically show is that the limiting distribution for this tau hat star, this Wald estimator, it is asymptotically normal, and that the variance is effectively exactly this kind of classic sandwich estimator. It's sort of exactly what the Ecker-Huber-White standard errors are typically used to estimate. They're slightly conservative under heterogeneous treatment effects, but the analogy here, it's exactly the same way that when you run an RCT, that you would typically just use robust standard errors, the Ecker-Huber-White standard errors, in order to estimate the standard errors for the average treatment effects. Really, there's no way in this setting in which clustering is appropriate. There's no reason to cluster on judge. And I'm emphasizing this point for those who don't potentially do examiner design, is because this gets done in practice. There's really no reason you would cluster on judges, in the same way that if you had an RCT, you wouldn't cluster on each treatment arm. So there's no inherent intuitive reason why you would cluster in this setting. You would simply just run robust standard errors. And empirically, I'm not going to show you these results today, but empirically it does matter. Like you have changes in the magnitude of your standard errors, both positively and negatively, depending on if you cluster versus just do robust standard errors. So that's one thing. And then the second is that, this result is we can allow for the number of examiners to grow with the sample size as well. Kind of we're allowing for this possibility that we're going to have many weak instruments as well. So that's the kind of the implication for inference. It's now let's kind of turn to thinking about what this estimand is, this tau. And as I mentioned, we're going to need some assumptions in this setting. So we're going to need exclusion and monotonicity assumptions. And so it's worth thinking about, well, what is the economic content of those assumptions in the case of this examiner design? Well, in our setting, the exclusion restriction basically assumes that the bankruptcy judge assignment only affects the outcome through the decision to discharge debt, whether or not you get treated or yes or no. There's no way in which the judge has this kind of additional impact on your outcome. And then the monotonicity assumption is assuming that judges have a common ordering on bankruptcy filings for who gets the discharge. So, there are a lot of very interesting recent papers that have attempted to test and weaken these assumptions. There's both in the monotonicity and in an exclusion setting. So Franzen et al. Have this paper. It's kind of the amazing title. It's the title that I would want if I was writing, if we were writing this as, judging judge fixed effects, which is to think about testing monotonicity and exclusion in this setting. And they propose kind of a weaker average monotonicity condition. It's kind of similar to tolerating defiers. There are also papers that try to parameterize the variation in examiner differences that try to estimate jointly these, basically the differences in examiners, as well as the treatment effects, is kind of some of the work that Peter has done as well in the bail setting. There's also ways in which you can kind of try and directly model violations of the exclusion restriction. So this idea that there's two channels in which a judge can have an effect. Can you try and model this and identify the multiple treatments that are going on? The challenge in this is that it's just harder to do IV with multiple treatments and get an interpretation of late. I mean, Alex has done some work on this, and it's non-trivial. So, the extent to which the exclusion restriction is violated, that's gonna cause potentially some issues. The last thing you could do as well is potentially weaken the exclusion restriction to being on average. This is kind of some of the work that Michael has done in the education setting, and as well as this Angrist et al. Paper. So in that setting, what you would need is exclusion restriction be uncorrelated with the leniency variation. And so these are all kind of ways to try and test and weaken these assumptions. For us, we're just going to assume that kind of monotonicity, or really what we're going to call weak monotonicity, holds, and the exclusion restriction holds. But I really want to kind of flag for researchers in the space that these are strong empirical assumptions. And so kind of amazingly, so Imbens and Angrist in their 1994 paper on late flag exactly this issue, that it's really not necessarily plausible that monotonicity holds here. So condition 2 requires that if official A accepts applicants with some probability and official B accepts people with probability greater than that, official B must accept any applicant who would have been accepted by official A. So it's really unlikely to hold, they think. And so it's sort of unlikely that this would work. So obviously that has not stopped many people, including myself, from writing a paper that does this, but it is clear that there's a kind of a strong empirical assumption there, and there are efforts to kind of weaken this. So what does it mean? So now that's like a very high level way in which I'm talking about what is monotonicity, what is exclusion. Let me just talk about like what it means formally in this setting. So what it means specifically, monotonicity, is that there exists an ordering, call it pi q, depending on the value of q, where you can basically say that if you take that ordering, that if you put them in a line, that if I get
I'm very sorry to interrupt. Could you please just wrap up in about 5 minutes?
Yeah, I'm gonna be done in about 5 minutes. Yes, I'm sorry, I didn't realize if I'm going. Perfect.
Thanks.
Yep. So basically, the idea is if we can have this strict ordering, that the idea is, look, if pi k is equal to L, then what that means is that the kth judge, k judge, is the L+1 least strict judge. It just means we can kind of take all 5 of us and we'll just put us in order, and that order kind of holds for everybody. No matter who gets assigned to those people, we kind of know exactly who's going to get treated and who's not. What we can show is that, so what's important here is that there exists this ordering, and that's about this pi ordering that exists about treatments that maps Q to relative treatment. With monotonicity and exclusion, the estimand is a weighted combination of treatment effects for these k different complier groups in this setting. This is very similar to this late theorem. And kind of the key result here is that these weights are positive if that D star measure, that oracle instrument, is increasing in pi. So really what it means is that whatever you're kind of getting in that first stage, especially even under the oracle setting, is that it needs to be increasing. It needs to be kind of mapping 1-to-1 with this true ordering that is satisfying the monotonicity condition. Now, this is satisfied with no controls under the oracle because the first stage prediction correctly identifies the right ordering amongst judges. I know who's lenient and who's not. I don't have to estimate it. I don't have to worry about it. There's no controls. It's all kind of, it's either there or not there, and they're going to map 1-to-1. Conditional on assuming monotonicity holds, DI star is going to be increasing in pi k. So I'll just kind of quickly say this, is that what you can do now and where the problems are going to arise is that if you let there be control. So basically now we're going to say, look, we're going to allow the probabilities to vary based on these controls. Well, this is a big issue. In most examiner designs, there are many controls. So like in our example in the Dabi et al. Paper, judges are assigned within an office within a given year. So we have like 1,500 fixed effects. There potentially could have been a lot more. And so as a consequence, it's important to think about having many controls and potentially many instruments. And knowledge of this PKW, thinking about what W is it a year? Is it an office month? Is it an office year? That's kind of key. This choice is where the decision over the time period to aggregate over is. That's kind of whatever you're conditioning on, this W is the relevant thing for conditional exogeneity. And it's what's giving you kind of your leniency measure. That these map 1-to-1 of thinking about aggregation. So in this setting now, what you need to do is you need to have a D star, the same oracle instrument as before, but it's going to be conditional on W. And so now what we need is a monotonicity assumption that holds conditional on W. And so we have the same pi k assumption. We assume, okay, exists this pi k such that monotonicity holds. And our assumption that we need is that this D star, this oracle instrument, maps with this pi W. And so the issue is that if our first stage is incorrectly specified, this condition may not hold. And this is true even if monotonicity is there. But if we specify our first stage incorrectly, and I'll get into how that could be in just a second, then we're not going to have monotonicity. And so what are the two ways? And so it's great that Alex is here. It's kind of misspecification of the necessary controls in the first stage. If you put in the wrong measures there, the inappropriate controls. So for example, if you need to do office month fixed effects to kind of correctly do this, but then you put in just directly office and year month fixed effects and not the interaction, that's kind of misspecified. And that's going to be wrong. And so this is in Alex's paper, they kind of talk about this. I'm not jumping the gun, I think. And then second is even in that setting, even if you correctly specify it, with multiple dependent treatments, we have this other paper about contamination bias that says if you don't do a fully interactive model, that is interact Q with W as a set of controls, you will have spillover across judges in the sense of what gets estimated, and you won't map to the true ordering, even under strong monotonicity. And so what kind of all, I'm going to stop in just a second, is what kind of all unravels here as a consequence is that once you realize you need to get D star correctly specified, that means you need to interact the judges with W. And once you need to interact the judges with W, you have this massive set of instruments and controls, which creates this important set of estimation challenges. And so let me just skip over that point. What all this is that inference, same points about inference show up with controls. Nothing changes in that setting. Clustering is inappropriate. So in this setting, if you have many controls, many instruments, well, we need UJive. And UJive is kind of, Michael has, his job market paper is kind of emphasizing this. This is a way to deal with these leave one out means of the controls. And some papers even do this already, but those papers still don't do the full interaction to solve contamination bias. And so now that we have to do that, UJive is a more functional approach where we have a beta testing package that basically does this. I'm putting this here in the slides. I think this will be recorded. But feel free to ping me. I'll put out I can send you the link if you want, where we have UJive working in Stata. And if you want to basically use this is a solution of if you're going to do examiner designs and you want to do this correctly, you're going to have many potential controls, many potential instruments. This is a very practical estimator to do this. So here is kind of the conclusion. Think about examiner designs as a many potentially weak instrument setting. Leniency measures are kind of convenient, potentially problematic way to do it. Work so far suggests that robust standard errors are the right way to do inference. And this is kind of at odds with the norm to double cluster standard errors. Finally, this accounting for the contamination bias in the first stage and kind of correctly satisfying monotonicity requires interacting instruments with controls, which means you should use something like UJEF. And I'll stop there. Thanks a lot.
Thank you. Thanks. Great presentation. Thank you. Thank you also for keeping the time now. So due to time issues, we had a debate in the chat. We'll probably open it also during the discussion. I would give now the floor also to Alexander Torgovitsky. Alex, I just provide you just a second. Yes, you should have the rights now, I hope. Sure. Great. Please just feel free to start. Alex?
Alex, we don't hear you. We don't hear you.
Alex, we lost you. It seems you have access to voice, but we hear each other, Alex? Yes, yeah. Slightly. Maybe if you speak a little bit louder.
How about that?
Great.
Yeah.
Yes.
Perfect. All right. I think after 2.5 years, we get this figured out, but
great.
Maybe not.
Thanks.
All right. So thanks, Andre and Peter, for putting together this session. This was really very interesting, a lot of fun. So this paper is with Christina and John. They're graduate students at Princeton and Stanford, and Magna is my colleague at Chicago. And so what we're looking at here are linear IV models. I'm going to say two-stage least squares, but actually for the talk, I'll be looking at linear IV as a sort of a special case of that. And in particular, the common interpretation of the estimands from these models as weights, or maybe weighted averages of weights. As you know, this is a key part of at least half of the Nobel Prizes here. If you read the scientific background the Nobel Prize Committee put out, it's discussed heavily. But if you look at the literature, you find very few theoretical results that accommodate covariates, which is a little bit at odds with common empirical practice. Paul was mentioning covariates are pretty commonly used in things like judge designs, as well as many other places. The one result that you will find commonly talked about is what Angerstein-Fischke and Leslie Harmless called saturate and weight. What that is a specification of two-stage least squares. You completely saturate on covariates. So you have a discrete covariate, you put in one indicator for each covariate value. And then in your first stage, you have a complete set of interactions between all covariates and all instruments. And so we had some questions about this. First question is whether anyone actually uses saturate and weight in practice. The second one was, if it's not the case, then does the late interpretation still hold? And then, based on the answers to those two questions, can two-stage least squares be interpreted as late in the types of settings we see in practice? So the answers to all those questions are no, shown in this paper. So I'll show you the results of the survey in a few minutes that show that nobody actually uses this, thinking this is harmless. I'll also show you that if you deviate from it at all, you get negative weights. And so you don't get a late interpretation. And so as a conclusion, the consequence of those two issues in most settings you see in practice, with a couple of exceptions that I'll mention, the late interpretation is brought as a result. Okay. So let me show you how we arrive at that conclusion in a simple setup. So you've seen this today quite a bit. We have a binary instrument, binary treatment. I'm going to call it T instead of D, but same thing. Outcome variable Y, and then some covariates that I'll call X. Okay, so the Imbens-Angus result the one that launched so many research ships, is this, right? If you have exogeneity and monotonicity, and you look at the usual linear IV estimand, which in this simple case is just a Wald estimator, Wald estimand, and that's going to be equal to the local average treatment effect, the average effect of the compliers. Okay, we've seen this, we talked about this a lot today. It's easy to extend this to conditioning on covariates. Just subset your data by whatever covariate value you're looking at, do the same thing, you're going to get a late conditional on covariates. So that's non-parametric conditioning, right? Conditioning on covariates in a non-parametric way. And nobody does that in practice because first dimensionality is going to bite very quickly the types of covariates that we condition on. So instead, what's more common is to control for covariates linearly. Right? So this is what you do in Stata, right? With IV regress, for example. Do an IV regression of Y on T and X where you're instrumenting for the treatment with Z. Right? So you have usual type of approach. A little bit of Frischwa. This is a great exercise to give to your undergraduate students if you want to torture them. You can show that the IV estimand, which is going to be this nice ratio, looks like a reduced form to a first stage, except now the instrument's been partialed out in the sense that we take the original instrument, subtract off the projection of that instrument onto the covariates, and use that resulting residual Z tilde, effectively the instrument. Okay. So the question then is, suppose we maintain, the usual assumptions imposed in the late framework, conditional on X, so the exogeneity condition, conditional on X. We have monotonicity condition. Here I'm going to assume that everybody's treatment choices goes in the same direction, meaning conditional on X goes in the same direction. There's other types of monotonicity you can consider, and talk about that a little in the paper. I'm not going to be very detailed about that today. But suppose you make those two assumptions and you look at this IV estimand that comes from the linear IV estimator controlling for X linearly. The question is, does that have a late interpretation? And the answer is no, not in general. So here I'm going to show you a little bit of a messy slide, but I'll walk you through it. So suppose that we make this additional linearity assumption for potential outcomes. It's not needed. It's makes the expressions a little bit simpler. I'm going to show you a negative result. So making an additional assumption is not going to make it. It's not going to help you, right? So suppose you make this assumption. Then, as we show, just by sort of cranking through the algebra, the IV estimand that I showed you on the previous slide, where we control for X linearly, can be written as a sum of two weighted averages. One weighted average is for the compliers. That's this thing. The weighted average of their treatment effects. Treatment effects are the delta, or conditioning on their group, complier, and their covariate value X. And then the second term is the weighted average for the always takers. Okay. So the weights here are these omega things. Here's the expression for the complier weights. Here's the expression for the always taker weights. I want you to look at the term in red for the always taker rate weights, this thing. The problem is that this thing is always going to be negative, except when it's 0. Why is that the case? Well, it's the difference between the conditional mean of Z given X and the linear projection of Z on X. As you recall, linear projection is the best linear approximation to the conditional mean. And so unless it's exact, meaning it's not an approximation, it's exactly the conditional mean, it's going to be an approximation, and so it's going to both overestimate and underestimate. Otherwise, it wouldn't be the best linear approximation. I mean, it's approximating in a square norm sense, right? Or square distance sense. So this thing is always going to be negative for some values of X, which means that we're going to have weighted average for the IV estimand, in which the always takers enter, and they enter with negative weight for at least one value of X. Okay. Always the case, except when the conditional mean of Z given X is equal to the linear projection of Z on X. Okay. Now, you might also get negative weights on the compliers too. If you look at this term in green here, that can also be negative. That's the usual saw about the linear probability model, right? That if you have a binary regressand, which is Z in this case, right? It's a linear regression of Z onto X. That can produce fitted values that are bigger than 1. So it could be that this thing in green is -2. But the key thing is that regardless of whether that's true, the always taker weights are always going to be negative for at least one value of X. Okay. So you need to have the conditional mean of Z given X equal to the linear projection of Z on X. We call that rich covariates. It's the name we developed just to talk about it more succinctly. And it's a necessary condition to get non-negative weights. And we show that quite generally in the paper. Now, there's a couple of cases in which you'll have that condition. One is in an experimental setting. So Stephen's paper, he talked about situations where you think about the instrument as being independent of X, which is often the case in many experiments. And in that case, this condition will be satisfied quite simply because the conditional mean of Z given X won't depend on X. That's the problem. Right? In other cases, if you use a very rich specification for linear projection, so in your IV specification, use a very rich specification, something like a saturated specification, like in the saturated weight argument in mostly harmless. And then a third case would be if you're willing to just make a parametric assumption that you specified the covariates such that you're going to reproduce the conditional mean of the instrument given the covariates. It's a strange parametric assumption to make, right? Because when you're writing down an IV model, you write down an outcome equation, and that sort of determines, you have a little bit of flexibility on what you set your instruments to be, but it sort of determines the first stage equation. But you're never writing down an equation where you have Z on the left-hand side. So this is sort of like an implicit parametric assumption you have to be making that it's not appreciated. Okay, so why is this a problem? Just take a step back. Well, remember why people don't like negative weights, right? So this is from a numerical example in the paper, simple numerical example. Here on the x-axis, we have the average treatment effect of the always takers, keeping the average treatment effect for the compliers fixed at 1/3, the same for all values of x. What we're plotting here is what the IV estimand is, as a function of the y-axis, the function of what the average treatment effect is for the always takers. So you can see first that, it's not a flat line. So the IV estimand depends on what the always taker treatment effects are, which if you like complier interpretations to IV estimates, that's bad, right? Because we'd like to think that only the people being affected by the instrument are showing up in the IV estimand. That's not what's going on here. And what's really bad is what happens in the shaded area. So in the shaded area, meaning this part over here, treatment effect for the always takers is positive, and the treatment effect for the compliers is positive too. It's a bit above 0 here, but the IV estimand is negative, right? And that's not a good thing if you want to think about this IV estimand as being a reflection of some sort of treatment effect, right? So this is, the usual story as to why people don't like negative weights. The difference in the event study, difference in difference literature that's been blowing up. It's the same story there. So this is just the same thing in an IV context, but this is why negative weights are seen as something that's not a good property for an estimand. Okay, so is this relevant? So to get a handle on that, we did a survey of IV papers with the empirical use of IV. We looked at 122 papers, the so-called top 5 journals. Most of them use two-stage least squares. Of the ones that use two-stage least squares, most of them either directly appeal to covariates, in the sense they say the instrument will be exogenous, conditional on these covariates, or they use covariates for all of their specifications. There's an additional reason you might use covariates, which is to increase precision, reduce standard errors, as in an experiment. But in these 99 papers, it doesn't seem like that's the only motivation. There's also some role for covariates to justify the exogeneity condition. And of those papers, a good chunk of them are explicitly claiming a late interpretation, roughly a third of them. Okay, so what type of specifications are being used in these papers? Maybe they're using saturated weight. Well, they're not. So of the 99 that we're looking at, there are some that saturate just in the covariates, which we have some results in the paper that show when that's okay to ensure positive weights. but they don't saturate in the instruments as well in the first stage. It's usually like a preliminary specification, but putting in a full set of fixed effects, for example. Not very many papers, but there are 5 who do that. And then how many do saturate and wait? Well, we actually only found 1 paper. I thought it would be 0, to be honest, but I found 1. And so the one that we found was Chamberlain and Imbens, 2004. So, Peter, you can ask Michael about this paper, or Paul, you can ask Michael about this paper. The point of this paper is it's not a empirical paper per se. It's a theoretical paper focusing on many instruments bias, which is naturally what you'd expect would happen if you do saturate and wait. If you're interacting the instrument with all the instrument values and all the covariate values, you're going to have an extreme many instruments problem. And so this paper uses it as a foil, right? Kind of ironically. And so no, nobody actually uses saturate and wait in practice, and there's good reasons that they don't do it. And so for all the 98 other papers, they're using something which potentially have negative weights for the always takers, pliers, or the fires, as I'll mention in a minute. And so yeah, we think this is a problem, potentially a big problem. Why have we reached this point? Who knows? But if you read some influential papers and books that involve one of the co-authors of the original late work, you'll find some statements that suggest that the saturate and wait thing applies more generally. And so we show formally in the paper that it does not. It's a necessary condition it provides, so it does not apply outside that case. But this famous handbook chapter by Angerson Kruger, which is very influential, there's a statement like this where feel like maybe hand wave a little bit and we can kind of like take this out to other settings. You find the same thing in Mostly Harmless. There's a fun typo here. So if you ever doubt if I've read Mostly Harmless, I read it so carefully that I actually know what typos are. And so this is kind of a revealing typo, but there you go. And then it gets reproduced, this type of intuition, this claim gets reproduced in other people who've read Mostly Harmless carefully, like in the Causal Inference mixtape. You'll find similar types of statements that have these few formal results, and then we can sort of extrapolate them to other cases, which we show is not the case. Okay, so what are the practical implications, and what can you do about this if you're a practitioner? Let me break it up into 2 settings. So one is heterogeneous treatment effects, which of course is what the whole Imbens and Angrist late stuff is about. So as we show, as I mentioned, rich covariates are a necessary condition. You could use flexible covariate specifications, maybe something which is more flexible than you'd normally think of, but not quite to the saturation case, which is often going to kill your standard errors. You might want to accompany that with some specification testing, like a reset test, although I'm not gonna go out and defend specification testing like this. Again, it's not a problem if you have an experiment. So if you think that the instrument is independent of the baseline covariates, it's not a problem, so you can ignore. And I'll say too, just mention here that given, so Paul mentioned this a little bit in his talk, even if you have rich covariates, there's still potentially some issues with monotonicity, whether you put in the right interactions in the first stage. And this has come up in the judge literature, as Paul mentioned, and also Timon Sochensky's paper, a very nice paper. So we cover this stuff too in the paper. I'm not going to focus on it today, but we have sufficient necessary conditions regarding that as well that basically generalize what Timon did. But that's all given rich covariates. So it's if you have this rich covariates, which you probably don't have, there's still potentially problems with the monotonicity condition. So suppose you get rid of heterogeneous treatment effects, you go back to constant treatment effects. Well, you're still not out of the water, right? I mean, you don't get a non-parametric causal interpretation for free. It shows you can replace the rich covariates condition with the assumption that you specified the outcome equation correctly. But that just goes back to like the traditional textbook interpretation of IV models, where what you're writing down is actually what you think is happening in the world, right? So it's completely getting away from this practice of reverse engineering some interpretation of an estimand in some other model that did not motivate that estimator. Okay. All right, so here's another solution. mind-blowing solution. There are other estimators besides two-stage least squares out there, right? Two-stage least squares is nice because it's easy to implement. We understand a lot about statistical properties. But as we're showing in this paper, I mean, if you want something that has a causal interpretation, non-parametrically, it's going to be tough in two-stage least squares. But there are other ways to estimate weights if that's what you want to do, right? Lots of ways. People propose many ways. Even authors of the original work propose many ways. Parametric ways, semi-parametric ways, non-parametric ways, machine learning ways. You could use one of these things, right? A different estimator, something designed for estimating a weight, acknowledging the issues with the parameterization going on here. And then, if you want to go that way and you want to actually talk about your assumptions and admit what assumptions you're making, well, maybe you don't want to estimate weights anymore. You want to think about, go back to first principles and think about, well, maybe there's a more clear policy question that maybe is not answered by a weight that I could go and estimate. Those are going to require assumptions too. What we're showing is that you don't get, there's no free lunch here, right, from two-stage least squares. So the story presented in Mostly Harmless is very incomplete. Okay, there's more stuff in the paper. I'll wrap up very quickly. There's more stuff in the paper. I pulled one over on you here a little bit. So I showed you an expression that had beta IV is equal to the sum of two things. Well, but you can write something as the sum of two things in many different ways, right? So to say that decomposition is not unique. And so requires a little more machinery as I think about all possible decompositions you could write. So instead of writing compliers plus always takers, you could write compliers plus never takers. What we show is that any decomposition you write is going to have the same problem. It requires a little bit more machinery, a little bit of theory, but it's in the paper. And the punchline is the same, that this rich covariance condition turns out to be necessary. We do it for multi-valued treatments, multi-valued instruments. And then we have this discussion about, specifying the first stage and how the covariates interact with the homogeneous decondition. Okay. We develop a decomposition that you can use to gauge the magnitude of how much these necessary conditions fail by in the particular setting. It's not super easy to apply, but we apply it to 4 applications. And we find some pretty strong evidence that what authors are estimating is often not something that's a causal interpretation. So this paper by Gelbach and this paper by Dubé and Harish, they use pretty rich, pretty complicated specifications of covariates with fixed effects in different ways, and so that it's impossible to fully saturate in fixed effects with the other covariates they're using. And we find pretty strong evidence there that the covariates are not rich and doesn't satisfy the necessary condition for a causal interpretation. Other papers, classic card paper, find something closer to rich. Angerson-Kruger paper, as you expect, looks fine because the instrument there is order of birth, which at least as they argue, and there's mixed evidence, but might think that's fairly well independent of baseline characteristics. Okay, so just to conclude, two-stage least squares is not late, okay? At least not without some additional parametric assumptions for using a flexible non-parametric specification. Is that surprising? I don't know. I knew the answer to this paper before I wrote it. Didn't know exactly how I was going to write it, but I knew this because we worked through the proofs. You find this stuff out, but it contradicts, common advice in practice and contradicts what you read in Mostly Harmless or Causal Inference Mixtape. These are necessary conditions. I keep stressing that because it sort of closes the book on this, right? It's a necessary condition, it's necessary. So you can't do anything else without it. It's done. As a more general point, this is all caused by this reverse engineering phenomenon, right? Where we start with an estimator, look at the estimand, what that estimator estimates, and then try and come up with a reverse engineering interpretation of it. Kind of a backwards way to think about doing statistics, but it's very popular. Has the virtue that you can stick with the code in Stata and then just change how you write about it, but it has serious limitations. It's very fragile. What can you do? I gave you a list of some things, but really it's, you got to use a different estimator if you want to call what you're estimating local average treatment effect. Okay, thanks. I went over by a minute or two, sorry about that. If you have questions, feel free to email me, and I enjoy engaging with emails. It's a nice distraction from referee reports, so happy to talk more offline.
Thank you. Great. Again, clap, clap. Great. Congratulations. Excellent talk. But I suggest there are questions in the chat, but I suggest due to the timing that we move forward, because in any ways we will have a discussion later. Peter, if you agree, maybe how to divide the discussion. As you mentioned at the start, we agreed that I shortly discuss the papers presented by Kirill and Paul, as Peter is co-authored there. I would shortly make a discussion of about 5-10 minutes here, and then you take over for the discussion of the papers of Stephen and Alex. Peter, is this okay? Great. Okay, thank you. As I mentioned, this is a little bit improvised. So I will basically just try to provide a few reflections and questions to hopefully stimulate the debate. Both papers naturally from that were presented by Kirill and Paul open, I would say, not just interesting and very frequently researched today, but also applied very important strategies for applied researchers. That's also one of the reasons, surely, why some of the people also attended the seminar. So the questions would be for Kirill. I mean, at least shift share instruments are, I would say, quite researched today. There are also data a little bit back, as we know, but are today even more frequently discussed. Firstly, in the announcement were mentioned other composite instruments. What other composite instruments exist? Possibly comparable with shift share? Could you list them? And maybe what are their properties and where could they be applied? I also listed part of this you already mentioned. So maybe how robust is shift share strategy that you also described in the papers to misspecification in the model and violations of the assumptions, the orthogonality assumptions it is based on, and have there already been developed some remedies, some solutions here? What are they? Next, again, in terms of the applications, the approach is mainly used in labor economics with applications, short applications also outside, I think, in international economics and otherwise. But could it be applied in general sense and outside of labor economics? Is it applicable also in any area of economics? What would be the possible limitations? I also state that it is based on regional instrumental strategy. The instruments are based on regions. Could extensions, say in the line of recent article of Florian Concilius on distribution synthetic controls, to distributional variables be used? And could some additional disaggregation in terms of the instruments be also performed here? Also, more generally, could any regression and treatment specification be shift share instrumented, and how? I think, like for Paul, this strategy could be compared to adaptive and banded multi-arm designs. If this is so, please explain. And could it be also extended to some machine learning strategies? What kind of them and how to work with them? And maybe I just additionally mentioned, you mentioned specification tests. You didn't have time, but are there any different as compared to other ideal situations? And what tests, one kind of specification tests to use here? For the poll, naturally both presentations were great. There was a question in the chat, but I nevertheless raise it about asymptotics of the problem. Perhaps you should additionally comment on how does your approach perform when number of cases per judge rises, as well as in terms of the clustering by judges. There were even other extensions, questions in the chat related to the asymptotics of this approach in different situations. Secondly, so maybe how is strength of the instrument determined in this case? Is this in any different situations? And for applied situations, how frequently would violation of the IV exclusion restrictions in leniency, judge leniency cases occur? Also, could your design be used in, say, both cross-sectional and longitudinal panel data, say, difference in different settings? So is it applicable in all, I would say, econometric modeling specifications. In your recent paper that you mentioned that is quite discussed in these days about contamination bias in linear regression with Peter and Mika Kolesar, basically you describe this bias related to heterogeneous treatment. How does the leniency design perform in the presence of treatment heterogeneity, and could leniency, as you shortly mentioned at the end, even solve for this contamination bias, while in the original article I think 3 different proposals are made. Like with Kirill, you already mentioned treatment arms could also this approach be compared to, say, bandit or similar adaptive approaches and other machine learning techniques. So could it be estimated by TMLEs or double debiased machine learning discussed today in econometrics related to machine learning, in terms of the applications and how to perform this strategy in different economic fields? And are there, like in shift share and labor economics, any areas where this would be more frequently suggested and used than in others? Also due to that issues I had here, I hope this to stimulate the debate. Thanks.
Thank you, Andre.
Karen, would you like to take a few minutes to respond and answer questions, and then Paul can, and then I can discuss.
Possibly, yeah.
Thanks a lot, Andre, for the question. So let me answer a few. There may be 1 or 2 which I didn't fully grasp, so would be curious later. So first of all, on your question about other composite variables, well, I kind of mostly talked about other composite variables today rather than the shift share itself, right? The market access and all of these, even though spillover regression that I mentioned, when the spillover is specified kind of in a linear way, like the number of traded friends, could be recast as a shift share, but needn't be. But indeed, there are many of these composite variables that we talk about in the paper with Peter, and you're giving me a chance to mention a few more. So, for example, one of my favorite examples is in political economy, where they're interested in the effects of media access, like TV access or radio access in some place. And so that is already viewed in that literature as coming from 2 sources of variation, from where the transmitters are, and then like whether from those transmitters they get to your village, or maybe there is a mountain in between. And so they view the mountain as exogenous, informally speaking, and the location of transmitters as endogenous, again, very informally. And so that's the type of composite variable we are talking about, again, where we say, well, if you want to use this, you better permute your mountains. They can't be just exogenous. They have to be relative to some counterfactual, even if it's a bit imaginary of how you reshuffle the mountains. These days, nonlinear shift shares are becoming more and more popular, with people trying to use the same technology, and I'll say a bit more about that now, to do more complicated things. Like I think Leah Bustan has a very nice paper predicting the Gini index for the region, not like an overall growth of something in the region, but the predicting inequality Gini index in the region from some shocks to income and some local shares. And then you can kind of compute a predicted distribution of incomes based on these shocks and take a Gini of that. Well, we're saying, well, that's a nonlinear thing. Again, it's not a shift share, it's a composite variable of a more general sort, which you need to recenter. So those are a couple examples on top of what I mentioned. And relatedly, all of this goes well outside labor. I mean, shift shares are used all over the place now. Let me give you an example in finance, for example, where a paper I quite like by Chen Zishu, who uses shocks to banks. Some banks randomly go bankrupt in 1865 crash in the UK or whatever, and then you can trace how those shocks affect different firms linked to those banks. So that's, you have the shares of loans from different banks and then the bank level shock. So that's kind of totally different setting. And why I think shift share is kind of and composite variables of other sorts are kind of interesting and important is because, going back to your question of like, where could they be used and so on, I use them as a translation tool. You have a regression, like a structural equation or causal equation that you're interested in. Okay, it's at some level, But then you've got a natural experiment, which is happening at a totally different level, not by regions, but by industries, not by firms, but by banks and so on. And so shift chair or any other composite variables allow you to leverage the natural experiment happening in one dimension to get causal estimates at another dimension, and then recentering is all you need to do it correctly. A couple more quick things. So you asked about misspecification. That's a great question, and robustness to it. One thing we can say is that the kind of control, for what we're doing, controlling from you, we probably recenter or control. So the controlling thing has this kind of double robustness feature. Maybe you're not sure how to specify counterfactual, so whether you're getting things right or not, but you can try a few times. You can propose a few different ones, compute mu of each, and throw them all in. And then if any of them is correct, or if there was no problem to begin with, because you didn't have this non-random exposure problem, in any of these cases, you'll be correct. Outside these cases, I think there is more research to be done about like which methods have less sensitivity when things are actually bad. And then finally, on specification tests, so you asked like, oh, how do they differ from others? So the specification test, which I didn't get to talk about today, is actually very simple, and it differs from the standard ones, I think, because it's design based. The idea is very simple, that if you did your recentering correctly, if you specified shocks, counterfactual shocks correctly, after you've done the recentered thing, market access, number of friends, street friends, or whatever, shouldn't be predicted by any baseline characteristics, right? And so it's a test of whether you specify the design correctly. You demean them appropriately, recenter, and then check that the market access is no longer higher in the east of China than west of China, close to Beijing, far from Beijing, for kids who have a lot of friends or a few friends and whatnot. So that'll be all.
Great, thank you. Thanks a lot.
Thanks for the questions.
Thanks. Maybe Paul, yeah.
Yeah. Let me kind of just touch on two of the things, because I think there's like things to be fleshed out, and like I said, it's sort of early stage. So let me touch first on thinking about this kind of this exclusion restriction violation. So that the easy offhand thing I would say is that's kind of application specific. So if you ask any one person who's written a paper on it, you'd say, well, don't worry, the exclusion restriction holds in my setting. So it's like, but to worry about other people's. But so in what we would say in our bankruptcy papers, we say, look, like bankruptcy judges, it's almost as if rubber stamping. That's why we sort of think of it as being satisfied there. There's some really nice work by Mike Mueller-Smith in the context thinking about criminal justice, where they're much more worried about the exclusion restriction being violated for a number of reasons. And so he does a lot more work modeling it there. And I kind of mentioned in the slides is, you have a bunch of different approaches, and it's kind of the most straightforward one is to kind of just model it directly. And I would say Peter's work with Will and Arnold is kind of trying to do some of that, of like modeling this more directly, what's going on. And you can make a lot of progress that way if you don't tie your hands to be fully non-parametric. So what I'd say in a short way is like, it's really challenging to do this. I think one thing that when I teach this, I say there is an element of, we've talking a lot about IV. IV, kind of the point is we want this one causal effect of a treatment. There is a lot of economic context where, irrespective of the IV aspect, the reduced form is quite interesting. So like judges, the fact that there's huge heterogeneity there, and the way that heterogeneity across judges has an impact. I try and emphasize when I'm teaching to my students is like, don't get too hung up exclusively on the IV part, because there's such interesting heterogeneity there, especially if you think there's conditional random assignment. So that's kind of the point that I'd like to say there. And once you start thinking about it that way, is you realize that's why this RCT intuition that we were saying of there's many arms, it's like an RCT, don't cluster on the arm necessarily, just do robust data. So that's the one thing about exclusion. That's kind of how I think about it. And what I want to use that is to talk about a little bit these asymptotics. So I kind of alluded to this idea that you could parameterize or additional assumptions. And this is a version, I'm going to give the very sunshine and roses version of what Alex was saying, but it's kind of this emphasis on the parameterization, because I think Alex, correct me if I'm wrong, but it's like, there's an element to which if we really are tying our hands to be fully non-parametric, like we don't want to make additional assumptions, it's quite challenging, especially as we start adding these things in. So the saturate and weight is just like very demanding on the data. Maybe it's like impossible because of course of dimensionality, et cetera. Now, what you could do is you make additional assumptions. And so part of the problem is people are not being explicit about that. But you could be explicit and say, look, we're going to model this. In some of these judge cases, for example, there's a question about this in the chat, is you could say, look, I need to be conditioning on within an office year. Like that's the random assignment. But like, obviously it's somewhat informative to think about what a judge behaves like next year as well as this year. Like, I don't want to exclude, like the non-parametric model would say, I need to interact the instrument with that year. And that's like my one cell. And that's what leniency is estimated off of. But you might imagine there's a certain amount of shrinkage or way that you'd want to use that across cells. That's an additional assumption that will potentially induce bias, maybe, or some other issues. But that's an additional assumption. So kind of the punchline is to say, in many of these asymptotic issues that show up, what we're kind of emphasizing is that if you're fully non-parametric, you start getting these like huge, tiny cell issues. Like you have small set, like a year, month by office, by judge is like not very many observations to estimate leniency. And so that can be challenging. And you need to be careful in how you do your estimator. But probably your intuitive statement would be to say, like, that's maybe asking a lot of the data, and we could maybe do a little bit more additional assumptions, not tie ourselves to the mast in quite the same way. And so that's what I want to kind of emphasize, is that I think a lot of this work that we're going to have here is going to be really saying, if you want to be fully non-parametric, you have to kind of be really demanding of the data, but maybe the right answer to that is not necessarily do that, but do that plus make some additional assumptions and see how far you can get with those additional assumptions. Anyway, I don't know if that kind of answered everything you described about other approaches, ML, things like that. Those all kind of tie into that space. I just don't know the answer. And that's pretty much it. Thanks a lot, Andre.
Okay, thank you. I suggest, we move on. There will be debate also later.
That was really helpful. Yeah, so let me just offer a few thoughts on Stephen and Alex's paper. So first of all, before I do, I just want to thank Andre again for putting this together and inviting me and inviting all of these wonderful scholars to share their work. I think, one recent trend in my view in econometrics and applied econometrics is this sort of emphasis on what practitioners actually do and trying to bridge the gap between what they do and this very long and rich history of, as Alex was describing, sort of, we know how to, in theory, do all these things, but bridging that gap between what people actually do can be a lot of work. And I think that's a very productive line of work, and I'm really happy to see it. So I have a few thoughts on Stephen's paper. I've discussed the paper before, so some of these might be repetitive to you, but so I am curious about, this non-binary treatment and instrument case. You already talked about this a little, but I think in practice, a lot of the papers today focused on binary D, binary Z, because that's sort of where we like to start from. But in the spirit of bridging the gap with practitioners, in many papers, it's more general. And I think it's important to, you mentioned the appendix sort of fleshes this out, but I think it's good to like maybe start there even. I am also kind of, this is going to relate to my questions to Alex as well, but I am curious about this idea of like the estimand changing as you improve precision and how you think about that. I know you do think about that in parts of the paper. I wonder how, if you were to talk to a practitioner and they ask you, how to apply your method, how you talk to them about the fact that like the late might be different, and how you sort of think of how to evaluate the differences, like the weights could or could not change the estimand depending on how strong empirically the correlation is with treatment effect heterogeneity. And, apart from the overall ML procedure to get your one treatment effect, it seems like you also have tools as a byproduct of that to characterize effect heterogeneity. And maybe there's a part of the procedure that can sort of give some guidance there as well. I'd be curious to think about that. I had another thought, but it's escaping me now, which is a problem for not writing things down. Maybe I'll switch to Alex, and then if it comes to me, I'll come back. So Alex's paper, I think is really helpful for, making very precise something which, like with several of these papers, I think has been sort of, as Paul said, like a folk theorem. Like Alex said, he knew it, before writing the paper. I think a lot of people have sort of, had these concerns about how applied people actually run IVs in practice, but it's nice to actually have a formal paper to cite about it. I've been working on negative weight stuff a little as well with Paul. You mentioned that paper with McCall on contamination bias. I'm really of two minds about it. Like on one hand, I think it's really important to establish what the potential problems are and make practitioners aware of what the problems are. On the other hand, just speaking personally, in a lot of the applications, it seems like it's not necessarily a first order problem. And a lot of that seems to be because even though there's a lot of treatment effect heterogeneity, even though there's negative weights, empirically the correlation between those things is not super strong in a lot of settings, not all, obviously, but and so, I'm happy to be proven wrong by that in any given application. And I need to dig into Alex's paper to really, I'm sure they establish this in the applications they have, but I think just like generally as a field, we should be thinking about, that next question, right? Like once we've established that, the linear regression, linear IB methods that practitioners are going to use have these potential problems, then we need to really sort of develop tools to make it very easy to check how first order these problems are. And I think the first step is showing the problem. The second is sort of showing how to go from there. I share Alex's view that there are alternative methods that work better. Big fan of kappa weighting and everything like that. But, I also share a point that Paul made not too long ago, which is that, in practice, those things can just be very hard and can lead to very large, standard errors. And there are some advantages of, linear regression adjustment for covariates, for example, if you think treatment effect heterogeneity is not super strongly correlated with the controls and, in terms of precision. And so, yeah, I think nothing I'm saying is new to any of the authors in this Zoom room, but just wanted to say that for framing, I'm curious to hear more about how both of you think of that, because I think it's kind of a related point between your two papers when it comes to thinking about weighting and how the estimand changes. But anyways, thanks again. Yeah, happy to hear your thoughts.
Yeah, no, thanks so much for the comments. I think it helps frame my thinking a lot around the things that I like to emphasize. I think I'm certainly I'm not comfortable with calling myself an econometrician because I'm really not. But I'm really more of an applied person who's interested exactly in this bridging the gap and thinking about what are ways we can improve the tools we have. And so I really appreciate this line of questioning. So thinking about say, for instance, a multi-value treatment in instruments, in the paper, we do generalize the results of the estimator when with the weights being known. The problem I think comes in where if you're estimating the weights non-parametrically and you have multi-valued instruments and treatments, we just haven't worked out how to get to asymptotic normality from there. Although that's certainly an avenue of future research would be interesting to explore. But I very much agree that and the results we do have, at least with fixed weights, suggest that the intuition very much holds in other settings. It's really just about focusing on where the instrument matters because everything else is just noise. And so I'd say my personal crusade, I suppose, is just against noise. I see is a big problem in practice in a lot of applied settings where ultimately the treatment effect estimates we come up with so many times are, well, so suppose you have a t-stat of 2 and you'd be like, okay, well, I'm pretty sure that the right answer isn't 0, but that's basically all you're saying, right? So I think, since we often operate in this sort of local to 0 treatment effect estimate world, if you will, I think that, in my mind, I'm really hyper focused on thinking about estimate precision, and sort of my mantra is sort of estimate well what you can, and don't try estimating things you can't, because ultimately you're not learning a whole lot from estimating things that you have no precision to do. Very much in line with what you're saying, and so it does require, as you suggest, thinking about estimate changes. Kind of choosing an estimate, which I think goes back to sort of the moving the goalpost paper by Crump and co-authors, and thinking about in just thinking about this as being a trade-off, between, how close is the thing you want to the thing you can estimate well, and kind of trying to exploit that. I do think what could be nice, where application-specific domain knowledge can be very helpful, are in perhaps identifying scenarios where, say, you have a credible reason to believe that compliance is not highly correlated with treatment effects, in which case you kind of have a free lunch by doing this approach. Like, you end up getting more precise estimates and you have the same estimate. But that's not always going to be the case, and that is like one of those things where that does require an assumption. But I think that's all I'll say for now, because I know we're running short on time. But thank you.
Okay, so just to respond to Peter's comment about so Peter mentioned he wasn't sure how big of an issue it is in practice. It sort of depends on how correlated the treatment effects are with other things. That's what you said, right, Peter? Yeah. But as we show in the paper, it's still a problem even if you have constant effects. And in constant effects case, the treatment effects aren't correlated with anything, right? Zero correlation with everything because they're constant. It's still a problem. You still don't get a free lunch. It's still non-parametric. Still need a parametric assumption. There's no non-parametric causal interpretation, even in the constant effects case. So why is that important? So I guess I really like Paul's comment earlier about being non-parametric is difficult. So sometimes you need to make some parametric assumptions to get somewhere. The question is whether you're making that explicitly or not, right? So you take a historical view on this. One of the claims of the so-called credibility revolution is that they're getting away from these arbitrary parametric assumptions that drove research before the credibility revolution happened. But that's not true, right? That's just because you're not stating what they are. It's not making the assumption explicit. And so for any type of causal inference, it's very important to make the assumptions clear and explicit so we can debate them and discuss them. There are parametric assumptions involved here. They've been embedded implicitly with some hand waving. So I think that's sort of the main point I take from it, is that, it suggests when you take that view that there's not this giant difference between the credibility revolution and what was happening before. It's just how explicit are we being about what assumptions are involved in the different aspects of it. Now, Peter's point is well taken. It's hard to know how big of a problem this is in practice. It's sort of fundamentally hard to know because, in order to really check, you want to estimate non-parametrically and compare that to what you're doing. And the whole point is you can't do that, right? So when I write other papers on structural models, I've written things where, you can do a parametric version, you can do a non-parametric version, you can compare the two. But in this case, the whole point is the non-parametric thing is infeasible. Now we have some tricks to get around that, sort of Hausman test type ideas in the paper. This is the decomposition I was talking about, which I didn't really go into detail about at all. And at least in the examples we find this is often a problem. These are just examples that we were sort of working on for other things that we had the data for. But it's natural to expect it would be a problem because when you think about all these covariates you're throwing in there, it's really hard to imagine interactions with various fixed effects and things like this are not going to have a first order impact. It's hard to even reason about what the parametric assumption you're making is actually doing.
Great, thank you. That's all really interesting. And yeah, thanks again, everyone. So this is recorded. It will be available on YouTube for folks who've missed it. Andre, do you want to say any few?
Maybe I would also open up the debate. If there is anyone, maybe raise your hand and ask. We will probably allow you to ask the questions. If there is anyone, there was a lot of the chat debate. We will try to put it online, but nevertheless, a lot of the questions already, I would say, answered. If there is anyone. If not, then I indeed suggest we end. Also in my name, I thank all the great speakers, naturally Peter for performing everything, inviting the speakers and for all the helping the seminar. Like Peter mentioned, this is already live streamed and it will be put online in about a few minutes, I think, on the YouTube channel of YoungStatS. So I would be very sure the responses would be great. I think the material is really great for anyone interested in the econometrics and IV approaches. So thanks greatly again to all, and to meet you on soon on some other occasion. Thank you greatly.
Thanks, everyone.
Thanks. Enjoy.